So I thought we might play a quick game of cut, bounce, or wiggle. It's an exciting new game. It's not that exciting. So what you have in front of you here are three types of cubic graphs. And they're the only types of cubic graphs. I mean, they might go in the opposite direction because of a reflection, so we can use that kind of language now. But more or less, these are the three types. And if we can start recognizing, oh, I've seen this kind of graph, and therefore I know what kind of cubic function it is, i.e. when I write the function out itself, then that's kind of useful, I think. If we can actually calculate what the, or work out, I suppose, what the cubic graph is, function, then that would be even better. Now, before I go any further, I should say that just to remind you that a cubic function is a function where if when you expand it or whatever else, the dominant term, the leading term is x cubed, something x cubed. Okay, so in the case of these three graphs here, if I knew what the function was and I expanded it all out, it would be something x cubed and then some stuff after it. F of x equals, of course. Okay, so the game. It's very simple. Is the graph cutting through? Is it bouncing on an axis? Does the graph have a wiggle? And it's not that good. It's not a game, is it? It's not that good. But here we go. Feel free to pause and do it yourself before you watch me. But yeah, here we go. In this graph, we have the line cutting through the x-axis, and it cuts through a second time, and then it cuts through a third time. Notice this doesn't happen in these two. Okay, so in slide 1 here, we have three cuts, three times cuts, three lots of cuts. For slide 2, we have just the one cut, and we have a bounce. So bounce and cut. So we have one bounce. Maybe I'll get rid of the x because it probably looks a bit like as if like a 3x or something like that. So we've got one bounce, one cut. And for graph 3 here, we've just got the one cut, then we have a wiggle, and then it keeps on going through. So we've got a wiggle and a cut. Now the wiggle, of course, is just a silly way of saying an inflection. So it's the one time in cubic graphs that instead of having turning points like here, like here, like here, and like here, we instead get a change in concavity. If you remember, that's what an inflection is, but it doesn't change direction. So it goes here. Okay. By the way, in this graph here, I just ran out of room, really. There is a y-intercept, but it's just outside what the graph is displaying. Okay, but there is one here. I don't want you to think there's no y-intercept. It's just like up here somewhere. Okay, so the reason why I got you to play that exciting game, and it was exciting, wasn't it? The reason why I got you to play that exciting game is because based upon that information, if you're looking at it, it'll give you a sense of what the graph is going to look like. So if it's got three cuts, then it means there are three linear factors that make up the cubic. So we've got linear factor multiplied by another linear factor multiplied by another linear factor, like so. If it's got a bounce and a cut, again, feel free to pause and sort of maybe work it out for yourself. But do you remember what a bounce means? It means that there is some repeated factor, so something linear squared, so like x plus 2 all squared, and then a linear factor. So every cut represents a linear factor for these two. And then if it bounces instead of cuts through, it's a linear factor. Now, if it's got a wiggle, then it's going to be a cubic like that, like a power of 3. Okay, So that's the three kinds. You can see that the x cubed would be found by going x times x times x will give me x cubed. For number 2, it'd be x squared times x to give me my x cubed term. And here it would be x cubed to give me my x cubed term. Okay, so this is the basic graph of f of x equals x cubed. But it's been transformed in some way, probably. So they're the three basic types. But the other thing we need to take into account, and I'll draw it and then I'll get rid of it so it's not too confusing, is that these three, if these three linear factors, for example, all just represent each of the different cuts here. So for example, that could be x plus 5, x plus 2, x minus 2, x plus 5, x plus 2, x minus 2, then we would get the same three things in brackets if we did something like this. Like that. Okay, it would be the same. I know I've gone off the track a bit here, but it would be the same x-intercepts, even though the graph is a lot stretchy. Or I could do sort of like a really low one, right? I could go ba 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 ba, and that would be the same intercepts or the same cuts here, here, and here, but it's all squishy. And of course, it could be quite the opposite, couldn't it? It could be like this. So in other words, these three things aren't enough to fully describe the graph, right? The graph might be squishied up, could be stretched out, and it could be flipped. So does that sound familiar to you? Does it sound familiar as a concept when we're squishing, stretching, or flipping graphs? Okay, if you're thinking transformations, you'd be right. Specifically, if you're thinking dilations and reflections, that would be awesome. So if we're ever trying to find a function given the graph, not only do we need to know some critical information about that written on that graph, but we need to know that we're going to come up with one of these two forms here, but we're also going to have to remember that there's going to be a value outside. Even if that value is just 1, we need to work out the value outside to determine if there's any dilation, and the sign of A will also tell us if there's a reflection. Okay, so when we're trying to work out the function from the graph, we need to be able to work that sort of stuff out. And we're going to go through an example of each of these so you can sort of see it in action. I was tempted to write, I don't think I will, I'll put it in just to show what I mean though. I was tempted to write that in for the cubic, but I just want to keep it blank like I have the other two. But remember that cubic has that kind of format for turning point form. Okay, it's a transformed cubic. Okay, so let's move on to the examples and then that'll do us. Here's the first one. So you do need to basically have a bit of information. So basically these three things here will tell us what the three linear factors are. And this thing here will help us work out the dilation because by knowing one other point, we can see how much stretched it is. And we can also work out whether it's positive or negative. So, we need one other point other than the other critical information. But we've got, as you can see, a graph that has 3 cutting points, and 3 cutting points means that it's going to be 3 factors, 3 linear factors. So we can go straight into our solution here. So we're going to have f of x is equal to a, because we don't know what a is yet. And then we're just going to have a look at each of the cutting points, and because they're, if you like, transformations of the input, we're just going to reverse that sign there. So we've got -3 as one of them, so it's going to be x plus 3. We've got -2 as another one, so we're going to go x plus 2, and 1 is the other cut through, so it's going to be x minus 1. Now note, we don't have to expand this. It is legitimately perfectly fine in factorized form. That describes the function perfectly. But we do need to work out what the value of a is. And so we use the fact that we've got -12 as our point here. It's very similar to the ones that we did with quadratics, really. So it's kind of same thing. And we substitute in -12 for f of x. That's the y coordinate, and the x coordinate is 0. So we end up with a outside of 3. You could do this in your head. I'm just spelling it out for the sake of it. -1 like so. So that's equal to -6a, which means that a is equal to 2. So therefore, the function is equal to 2 outside of x plus 3, x plus 2, x minus 1. And that's basically it. We're done. That's sorted. Okay, second example. I'm just using the slide from the first page there with numbers written in. So sorry for it all being written all over the place. It's just I couldn't move the slide over. So in this instance, we can see that we've got a bounce, and then we've got a cut through, and we've been given one other point. So we start off with f of x is equal to, and then I know I'm going to have some sort of dilation I have to figure out. Then I'm going to have my square factor, and then I'm going to have my cut through. So the bounce is at -4, so it's going to be x plus 4 all squared, and then the cut through is at 1, so it's going to be multiplied by x minus 1. And again, we just need to work out what A is, the dilation and reflection. So we're going to substitute in the other point we know, which is 0, 4, the y-intercept. So I substitute 4 for f of x, which stands in for y, and I substitute in 0 for x. Oops. And I solve that one. 0 plus 4 is 16. 16 times -1 is -16a. So I've got -16a. So divide both sides by -16. Just be careful that you're dividing a smaller number by a bigger number, so you should get a fraction. Don't accidentally go 4 goes into 16 4 times, something like that. So we've got a is equal to -1/4. You can very happily put in -0.25 if you prefer. So therefore the function is equal to -1/4 x plus 4 all squared, x minus 1. Done. Okay, last example is an inflection. So what we're going to do now is we're going to use our knowledge of inflections in order to write this down. Sorry that the lines are missing here, but I'll just write up the top anyway. So we've got f of x is equal to a outside of x minus the x coordinate of the inflection point. So it's going to be x minus 3 all cubed plus the y coordinate of the inflection point. Now the y coordinate is -4, so adding -4 is the same as subtracting 4. So we've got a outside of x minus 3 all cubed minus 4. Now we're going to use, we don't have the y-intercept in this instance, but we do have one other point. So we substitute in the y coordinate, which is 4, and we substitute in the x coordinate, which is 1, and then we can solve for a, just like we have done in the past. So I'm going to go 1 minus 3 is -2 cubed is -8. So I've got -8a minus 4. I'm going to add 4 to both sides to get 8 is equal to -8a. So a is equal to -1. Okay, so therefore f of x is equal to negative, you don't have to write the 1 in, negative x minus 3 all cubed minus 4, and we're done. Okay, that's all I want to say. I've got a little bit of an addition to add here, but pretty well much, if you stop the video now, you should be right for any graph that you come across that's in cubic form. So number 1, is it a cubic graph? If it is, what form is it? Does it cut? Does it bounce? Does it wiggle? It'll never wiggle and bounce, for example. It'll never cut more than once and then wiggle. Okay, so it's always just one of those 3 combinations, 3 cuts, a bounce and a cut, or a wiggle and a cut. And that's the only 3 options that you've got. If they satisfy that, it's going to be a cubic. So keep that in mind. A little bit of an addition now. So if you stop the video now, that's absolutely fine. But just in case you're thinking about it, this is the form that I've left it in. And you may be asking, why we don't have to worry about the b inside of the bx. So in a full transformation, we've got a outside of bx minus h all squared plus k. That's the full transformation, and I didn't get you to consider b at all. And look, the reason is a little bit tricky, but I'll try and do it by example a little bit. So if I have f of x is equal to, I'll try and make it easier on myself just to make it straightforward, because I'm actually thinking about this as I'm doing it. 2 outside of 3x minus 1, sorry, that should be a cube, cubed plus 5, something like that, right? Well, technically, this little bit here, the b value, could be factorized out. So I could go 3 outside of x minus a third cubed plus 5. And because I've now got two things multiplied together here, the 3 and this thing here, I could go 2 multiplied by 3 cubed multiplied by x minus a third cubed plus 5. 3 cubed is 27, so we've got 54 outside of x minus a third all cubed plus 5. Okay, what I'm trying to say is that with some trickery, not really trickery, but with some manipulation, I suppose, the b can effectively be brought out to the front of the function, so it kind of effectively just stretches out the graph. You can't do it under all circumstances, but for every single function in the world, but it certainly works for polynomial functions, that a stretch away or towards the y-axis can be kind of factorized out, so it becomes a dilation outside the cubic. It means the number inside could be really scary. Like, this is not too bad because I artificially made it not too bad with just a third, but you could imagine if I was taking out another number, you might be left with 0.71211798 or something like that inside. So it's not really what we would normally do, but we certainly can do that. So why am I telling you all this? It means that operationally, I don't really need to look for B, because ultimately, if I just work out what A is using this process, even if there was a dilation of the input, it's kind of, it doesn't sound great, I know, but it's kind of captured outside the bracket anyway. Just like this is a dilation of 54, but really it's a dilation of 2 with 3 on the inside. So it's kind of a bit captured there, I suppose, in a way. So I will leave that there as something for you to ponder. You don't have to really think about this at all. It's just enough to know that you can just basically always follow this process and it will always work. Okay, try some yourself from the textbook and we'll go from there.